Hi, my name is Manish Gupta, and in this video, I'm going to talk about our recent work on circuit VQA. This is a visual question answering dataset for electrical circuit images. Okay. This work is in collaboration with Rahul Mehta, Bhavijit Singh, and Professor Vasudev Verma. Rahul and Professor Vasudev work for IIIT. Bhavijit and I also work for Microsoft besides IIIT Hyderabad. Okay. So this work is going to be presented at ECML PKTD 2024. Okay, so let's get started. Why should we do visual question answering for electrical circuit images, right? And what is it? So let's talk about that. So here is an electrical circuit image. So as you see, there are several resistors and battery and inductors and transistor and whatnot. Okay, so on this one can actually ask these kinds of questions. Simple counting question. What is the total resistor count within the circuit? So you should basically count this guy and this guy and this guy and this guy and so on and this guy and then say, hey, five resistors. Okay. There could also be spatial counting kind of questions. How many voltage DC are connected directly to the left of inductor? So this is the inductor to the left of this guy. Well, there's only one, so that's that. What is the value associated with the voltmeter? Okay. So the voltmeter basically reads 12 volts, so that's that. Can we observe a transistor.BJT, a special kind of a transistor between junction 7 and junction 9? Okay. I need to figure out where is junction 7, so that's that there, and junction 9. So essentially, what is the question again? Can we observe? So yes, there is a transistor. Of course, there's a transistor out there. And then, can you tell me which circuit component is at the leftmost position? So, and here there is some sort of crossovers which are going on in the leftmost position. So crossover is the that, right? So those are the kind of questions which I basically call as visual question answering for electrical circuit images. Now, these kinds of things are useful in several scenarios. They could be useful for students, as a teaching tool or a quiz generator for students who are learning about electrical circuits, provide feedback and hints to help students solve the circuit problems. Uh, well, the question answers that you see here are very preliminary. They're not really like applying Ohm's law or Kirchhoff's law and so on, but still, at least they're at least to a certain level, useful. Okay. Design assistant or a verification tool for engineers who are creating or modifying electrical circuits, suggest improvements or optimizations for circuit design, debug or diagnose. Diagnostics tool for technicians who are repairing or testing electrical circuits, identifying faults or errors in circuit functionality, accessibility tool for visually impaired users who want to learn about electrical circuits, analysis tools for researchers who want to study or compare electrical circuits. So several applications of doing visual question answering on electrical circuit images. Okay. Although there is a whole bunch of related work on visual question answering for science, there was absolutely no work on visual question answering for electrical circuit images. And that is why we thought we would do this work and contribute the data set to the community. Okay. So people have worked on science images, several scientific images like diagrams, graphs, charts, and illustrations. For example, there are these data sets, Science QA on science lectures, AI 2D on diagrams, Chart QA on chart summaries, Figure QA on line plots, dot line plots, vertical and horizontal bar plots, pie charts, DVQA on bar charts, plot QA on plots, leaf QA on figures, charts, BizGraph QA on graph structured diagrams from business domains. Okay. Um, there is also, and as I mentioned, right, although all of these things exist, there's absolutely nothing for electrical circuit images, and that is why we do this. We did this work. Okay. And now let's talk about machine learning for electrical circuits. So people have been trying to apply machine learning for electrical circuit analysis. So prominently, there have been attempts to do electronic design automation tasks and electronic circuit design using machine learning. Specific tasks include recognition of hand-drawn electrical and electronic circuit components, and also fault diagnosis of analog circuits, finding faults in those circuits. Right? One yet another interesting area is about hallucinations in images. So or hallucinations in terms of vision language models. So in this case, our input is going to be an image and a question, and the output is going to be a text answer. So there could be hallucination, right? And interestingly, although people have tried to come up with such hallucination for visual language models, they have never done anything for visual question answering. So therefore, in this paper, we also define a specific metric for sort of estimating for measuring hallucinations for vision language models. Okay. So hallucinations are essentially contradictions between the visual input taken as fact and the text output of a VLM, of visual language model. And existing approaches are CHAIR and POPE, right? They try to figure out hallucinations in terms of missing objects or newly discovered objects in that sense, which don't exist in the image at all, right? But as I mentioned, there's nothing for visual question answering, and that is why we fill this gap in this paper. Okay. So to be able to create this data set, we actually leverage 5 different data sets. Okay. So we actually make use of these 5 different data sets sourced from RoboFlow and Kaggle websites. Okay. Some of these data sets, as you can see, are schematic in nature. The others are hand-drawn. So they're hand-drawn as well as schematic data sets. The number of images are in a few hundreds. The maximum is 2,304, but the minimum is 487. Okay. These data sets basically have images, and they also have annotations for various objects of various components in these images. For example, the 7 components labeled in this data set, 59 here, 14 there, 7 there, and 45 there. So what kind of components? Well, these kinds of components. So resistor, current source, inductor, capacitor, the kind of electrical components that you can expect in these images. They're labeled in these data sets. Okay. So these data sets, all these 5 actually are derived from a central data set called as handwritten circuit diagram images data set. And then there are these variants. Okay. So what we did was to basically take these data sets which contain images, human-annotated bounding boxes, and corresponding component classes. We deduplicated, we of course combined all of them, deduplicated the images, and then finally we get a unified data set of 5,725 images, of which 3,175 are hand-drawn and the remaining are schematic. Okay, so that's the data set. Now, what we want to do is to actually build question answer pairs on top of this data set so as to train visual question answering models. So the first step is to actually create question templates and try to figure out what kind of questions make sense when you try to do visual question answering on electrical images. Okay. So we first try to figure out and brainstorm that these 5 question types are important: simple counting, special counting, value-based, junction-based, and position-based. We saw the example on the first slide itself, right? Uh, so we considered 5 different types of questions. For each type of question, we actually obtained question templates using ChatGPT. So what you see here are question templates using ChatGPT. Okay. For example, simple counting, how many X's are there in the specific circuit? X is, of course, a placeholder. It tells you, a particular component should be there. How many resistors are there in the specified circuit, for example, right? All these paraphrases are actually obtained using ChatGPT. Okay. Similarly, there could be other templates like how many Y are connected directly to the left of X. So you have basically, 2 components, X and Y, placeholders, and that's why this template. What are the current reading displayed by the XX? Yeah, it could be ammeter or voltmeter and so on. Does a X exist between junction Y and Z? So you have like a template with 3 different placeholders, X, Y, and Z, where Y and Z are junctions, X is an electrical component. Which circuit symbol is on the far X? So here X basically would mean left, right, bottom, or top, right? Which circuit symbol is on the far right, far right, far left, and so on. Okay. So we use ChatGPT. I'll detail more, how do we use ChatGPT to generate these question templates, but use ChatGPT. And then the idea is that you instantiate these questions using these templates, instantiate questions using these templates. We randomly choose a template, for example, to create a position-based question, and then use the image metadata like associated components and their bounding boxes so as to actually create those questions. That's basically the way we use question templates. Now let's talk about each of those question types one by one and try to understand how do we create the question templates, questions, and then answers. Okay. So for example, simple counting questions, the aim is basically to ask for the count of each component type in the image. And ChatGPT basically is used to generate question templates like that. Paraphrase the following text in 20 ways. How many X does the circuit have? Right. Of course, to generate a question, we replace X with the actual component name from metadata. Metadata does contain component names and their count, so therefore the answer can be directly derived from the metadata itself. Okay, and these kinds of questions, when you build a visual VLM, vision and language model, right? So these kinds of questions are going to test whether the model has object recognition and counting skills or not. Okay. Spatial counting questions, these questions ask how many components of a certain type are connected directly to the left, right, top, bottom of another component. Okay. Now there are multiple data sets, and the data sets, by the way, an interesting part about these data sets, this data set is on digital logic only. So you see, these the components are just digital components, okay, digital logic components in that senses. While other data sets basically may contain some digital logic images, but prominently they are typical electrical equipments like resistor, diode, transistor, and so on. Okay. So for D1, D2, D3, and D5, we prompt ChatGPT using this template. How many Y are connected directly to the direction of X, where direction could be right, left, left, right, top, and bottom. For D4, which is a data set about digital gates, we basically just we don't really use templates there. We just manually design these templates. We didn't use ChatGPT, we just manually designed these templates. Okay. Of course, to generate questions, we instantiate the templates by replacing these placeholders X and Y with the actual component name or the direction, with the actual component name, and also put the direction appropriately. The answers cannot be directly derived from the metadata in this case. So therefore, human annotation was done to get the answers for those questions. If a model has to work nicely on these kinds of questions, it must be able to do object detection and localization. Okay, it has to figure out spatial kind of reasoning. So therefore, localization skills are also needed. Right? Value-based questions. Well, these questions ask what is the value associated with a particular electrical component in the image. So we again use ChatGPT to create question templates starting from this seed template. What is the reading on X? Okay. So we provide a list of all values as the answer. So if a particular component, let's say resistors, there are like 5 resistors. So then what is the value associated? We must list down all the 5 values because that's what is expected. We tried to actually use OCR so as to figure out those values automatically from the images, but we are not able to do that accurately. I mean, the accuracy with these OCR APIs is not that high. Okay. Also, the metadata does not contain this answer. So therefore, again, for this kind of questions, we had to do manual answer labeling. Okay. To be able to correctly answer these questions, the model needs to have optical character recognition, OCR skills, object recognition skills, and also the capability to link text labels with the components. Right? The fourth type of questions are junction-based questions. So these questions ask whether a component exists between 2 junctions. Okay. So data sets D2, D3, D5, fortunately, they themselves have labeled bounding boxes for junctions. So that helps basically get the junctions for us. And then we use ChatGPT to paraphrase this C template. Does a X exist between junction Y and junction Z? Okay. Now, getting these templates is great, but then how do you really instantiate these templates? So we first randomly choose a junction Y. So given an image, we just randomly choose a junction Y. Then we choose junction Z, which is closest to Y. So just to avoid any issues in that sense, you basically want the closest junction to Y. Okay. And then we basically, junction-based questions are binary questions. So binary answers, yes or no answers, right? So therefore, what we do, we have to sample a positive kind of X, some X, which basically makes it a positive question, some X dash, which makes it a negative question, okay? So to basically choose the particular component X such that it is positive, we basically compute Euclidean distance of every component from these junctions Y and Z. And then we choose that particular component X such that it is closest to these junctions Y and X, such that it has the minimum distance to these junctions Y and Z compared to any other pair of junctions. So we choose a component for which Y and Z are the closest junctions as such. Okay. So that's that. Again, for negatives, we'll randomly sample some component X dash, which is different from the component type of X. So if X was a resistor, we try to make sure that we choose something which is a non-resistor randomly sampled from the entire image. Okay. So again, to be able to answer junction-based questions, they're sort of difficult. You need object detection localization skills as well as spatial reasoning skills, understanding where are these junctions and what is the component in between. Okay. Lastly, position-based questions. So we know so basically the idea is to ask what is the component at the leftmost, rightmost, topmost, or bottommost part of the image, right? So again, we use ChatGPT to paraphrase this basic template, which is the X-most circuit symbol. So X could be left, right, top, or bottom. And for the answer, here the answer is automatically generated. So we use bounding boxes of the components to decide leftmost, rightmost, topmost, or bottommost components in an image. And if there is no unique answer, we eliminate those questions, right? So that's that. Again, to be able to answer these questions correctly, the model must have object detection and localization skills. So overall, net in summary, we have 5 different question types. The simple counting is count-based, special counting, again, count-based answers, junction-based are binary answers are expected, yes or no. Position-based expects component name as an answer. Value-based questions basically expect a list of values with units as answer. Okay. So these are the stats in our data set. So as you can basically see, there are a whole bunch of junction-based questions. while on the other hand, the spatial counting-based questions are not too many, but overall the data set actually contains quite number of questions. So 115 or almost like 116,000 questions. That's huge, right? And again, basically they cover great number of images, right? As I mentioned, they cover like 5,725 images. So overall, the data set is pretty large, pretty nicely thought through, and in the construction of the data set. Okay. So now, if you basically look at value-based questions, amongst those value-based questions, registers, ground, AND gate, NAND gate, inductor, these are the most popular questions. These are the most popular components in those value-based questions. Okay. Also, if you look at count-based questions, although many questions have just one, many images have just one, or rather many of these count-based questions have count equal to 1, but it's not completely biased in the sense that around 52% of those count-based questions still have the answer count greater than 1. So it's not like if you just choose the 1 as the count always, you will get like 100% accuracy or close to that. You'll basically just be able to get like 48% accuracy in that sense, right? But because 52% have count greater than 1. Okay. So we leverage several multimodal models for solving this problem. So they are shown here. So we leverage generative models as well as instruction-tuned models. So generative models include BLIP, Git, and Pix2 struct. And instruction-tuned models include Lava, Instruct, BLIP, and also GPT-4V. Okay. Now, here are details about the architectures of these models. So I think those details, yes, I mean, of course, BLIP is BERT plus VIT for image encoder, and the decoder is BERT base. And then these remaining models are all decoder-based models. There's no text encoder. And typically BERT or Llama or Vicuna is used for text decoder. VIT is standard used for essentially as the encoder, image encoder, right? And then they have their own pre-training objectives. I won't go over those. But what is important to notice is the size of these models, right? So essentially, Lava and Instruct BLIP are effectively instruction-tuned models, and therefore they are pretty large in size, about 7 billion parameters, 8 billion parameters, and so on. Of course, GPT-4V, we do not know exactly how many parameters it has, but it is pretty large, right? About more than trillion parameters for sure. Okay. To train these models, we fine-tune them using language modeling laws. So that's that. Okay. So how do you represent the input? So of course, the image should go as input, the text, the question should go as input. What else can you send as part of input? So you could also send the OCR text from these images, extracted from these images as additional input. So we ran Google Vision APIs just to extract OCR outputs from these images. And we also passed that as an extra input to these models so as to predict, so as to come up with the good answers, so as to come up with the right answers for these questions. Okay. However, these OCR texts are noisy. So therefore, what we also tried, we have of course tried all of these variations. So we report results using the base model, using OCR text, OCR post, bounding box based models, and so on. Okay. So OCR text is noisy. Therefore, what we also do is OCR post kind of model where we only keep the numbers and units typically expected by electrical measurement. So we only keep those OCR output tokens that contain any of those, and you can sort of relate with them, ohms and so on, those typical electrical units, right? So you keep only those strings or a combination of these strings with digits, basically. That's all we keep as the OCR output tokens. Others we basically eliminate. Okay. So that's one kind of input. The other kind of input that we can supply is bounding box information. So what we do is to use these. So some of those data sets have bounding boxes. So we use those human bounding boxes in the metadata to fine tune YOLO V8 object detector. That basically helps us get bounding boxes on all the images, right? It is basically trained for all of these classes. Of course, I'm not going to read over those classes, but as you can see, those are all kinds of electrical equipments that exist in our training data, in the training data of those data sets which had bounding boxes labeled, right? The bounding box predictor that we have trained, object detector, actually gives us reasonable precision of 78, recall of 64, a map 50 of about 70, and map 50 to 95 about 51. Okay, so it's a reasonable bounding box predictor in that sense. So how do we use this bounding box to decide the input information? Well, we can actually, for each detected component in the image, we can actually give the component name and X, Y, WH coordinates for the bounding box. X, Y is the center of the bounding box, rectangle, right? And W is the width and H is the height. So you could give these. Or, sometimes these coordinates are too specific. So what you could do is to generalize and give bounding box plus segment indication. So assign each bounding box to one of the 9 segments, indicating the location of the bounding box relative in the image, right? So the bounding box could be upper left, upper middle, upper right, left, middle, right, left, lower middle, lower right, right? Any of those. Okay. So, and in this case, in this particular variant, we basically pass the component name XYWH as well as segment name. Of course, we pass on the image itself and image embedding and the question embeddings as input anyway. Okay. Lastly, we could also get a visual description of components. So what we did was to first figure out in this image what all components are present. We went to ChatGPT and generated electrical components description in 50 words. For example, for capacitor, this is the description that ChatGPT generates, symbolized by 2 parallel lines with a gap. It stores and releases electrical energy, acting as a temporary energy reservoir in a circuit. Okay. So this is the extra description that we actually pass along with the question in this kind of input representation. Okay, so all the components that are present, we basically take the electrical circuit components visual description and pass that as input in this description-based method. Okay, so yeah, so that's that. Now, you see, I mean, these are basically the input prompt templates for instruction-based models. Essentially, we use Lava, Instruct, BLIP, and GPT-4V, and these are the prompt templates when we have different variants of inputs being passed. Okay, different variants of inputs being passed. And as you see, they all make use of various kinds of information like component name, ChatGPT description of the component, bounding box coordinates, or OCR text as well, OCR information. And of course, they always contain the question anyway, and the image as well, right? So here are the results, okay? So, and before I get into results, let me just talk about our new hallucination metric. So our HVQA metric is basically a combination of 3 different HVQA scores, hallucination for VQA scores. Okay. So first, we basically care for hallucination in terms of count. So it captures overcounting of existing objects. So for simple, and it's applicable for simple counting, special counting, and value-based questions. Okay. HVQA in domain basically captures predictions of non-existing in domain objects. So, in predictions, you basically get those in domain electrical objects which are non-existent. That's counted in HVQA in domain. That's a hallucination of objects, in domain objects, right? But sometimes out of domain objects can also be predicted by these models. And that's basically HVQA out domain. It captures predictions without hallucination in terms of predictions with out of domain objects. Okay. Now, of course, the HVQA in domain and out domain are applicable for position-based questions. Okay. So here are the results. So these are the main results. They basically compare different models, and they also compare across different, input types. Okay. So what you observe here, and basically what is shown is accuracy and the HVQA, the hallucination scores. Okay. So what you observe is that typically BLIP gives you the best accuracy results across different methods, right? I mean, across different methods, you see BLIP is performing well. So a BLIP performs specifically well on the description kind of method, right? So where you also pass on the description of the electronic components with the input. Okay. So BLIP provides the best accuracy, while Lava and GPT-4V, if you look at them, Lava and GPT-4V, they typically provide the least hallucination scores in that senses. Okay, so that's that. Now, the best model amongst all of these is the fine-tuned BLIP when it is paired with prompt of visual description of the component. So we call it BLIP desk. Okay, so BLIP desk, which is basically description. So this one, right? This one. Its hallucination score is not the lowest, but it is pretty comparable with the hallucination score obtained by Lava. Okay, so it also hallucinates less on in-domain objects compared to its fine-tuned component. So other tables basically show you other views. For example, this table actually shows a view which compares these models with the types of questions. So as you can observe, BLIP model, and this is for the description variants. So as you can observe, BLIP model really performs very well for junction-based questions, but it does not really perform very well for value-based questions, for example, right? So similarly, this table actually shows to you hallucination scores. So as one can look at from this perspective itself, GPT-4V hallucination is pretty low in that senses, right? The lowest, in fact, right? However, BLIP model hallucinates, but not too much, right? So essentially, BLIP model's hallucination is, in fact, less than the hallucination of Git and pix2struct in that senses. So, so it hallucinates less on in-domain objects compared to, so yeah, so I mean, for in-domain objects, its hallucination score is lower. But yeah, I mean, if you look at count-based objects, its hallucination score is actually higher compared to Git and pix2struct. Overall, net, if I basically look at, this one, 5.5, it's actually lower than 6.7 and 6.1. Lower the better. Hallucination score, of course, you want less hallucination. So lower the better. Okay. So fine tuning in general, if you observe these fine tuned these are zero shot models, and the above ones are fine tuned models. So fine tuned models basically broadly ensure that they do not hallucinate on out of domain objects. Okay. So if you observe out of domain objects, there is just no hallucination. So C basically is out of domain hallucination. In domain hallucination is B, and A is count based hallucination. So you observe that fine-tuned models do not show any hallucination for out-of-domain objects, but zero-shot models like Lava instruction-tuned models, right? They showed out-of-domain objects in the output, like circle, square, ABDF, triangle, snake detector, snake. All of those basically are shapes that look like our electrical components, and therefore Lava ends up predicting them. Okay. Here are some examples of predictions from our best model. So these are three images, A, B, and C from the data set. And you can basically take any example. Let's say how many components are there in the circuit that function as ammeters, and that's A. So A image only has one ammeter, so the answer is 1. Okay. Similarly, there are other questions. Let's say, is there a transformer interposed between junction 37 and junction 36? So you need to figure out where is 37 and 36. Yeah, that's there. And yeah, there seems to be a transformer here. So therefore, the answer is yes. Okay, that's that. Okay, so but the model of course makes errors as well. So we tried to do very extensive error analysis to figure out what's going on wrong. Here are some examples. In fact, we did a manual analysis of 100 cases, right? So 20 of each question type. We found that value-based questions typically, when it went wrong, it came up with wrong units in 4 cases out of 20. 11 cases out of 20, it came up with incorrect values, and 5 cases, both the units and values were wrong. Junction-based questions, basically, it came up with the wrong results in 12 cases in images containing more than 40 junctions. While in 8 cases, it came up, it basically led to errors with less than 40 junctions. So generally, we observe that more the junctions, yes, the complexity of the answering sort of becomes difficult, and therefore, it does make errors. Position-based questions, 9 of them basically predicted component, which was physically the second closest to the correct component. So 9 of them were like near misses in that sense. 11 of them were actually far misses because predictions were far away from the actual component. Simple counting questions, 11 of them were overcounting, 9 of them were undercounting. Overcounting basically was within a range of 1 to 5, so not too much over. Special counting questions, 4 of them were overcounting, 16 of them were undercounting. Okay. Okay, so here are some examples as well. So there are these 3 images from the data sets, and these are examples of errors that happened. So junction based, is there a capacitor between junction 18 and 16? So this is image C. So 18 and 16. Let's see, where is 18? Where is junction 18? Oh, junction 18 is there, right? And junction 16 is there. And in general, there is no capacitor in between. So the right answer is no, but the prediction is yes somehow, right? So there are these some of those error cases. You can pause the video to look at them more, right? But that's that. So in summary, in this video, I talked about our recent work on electrical VQA, where we propose a new problem, visual question answering for electrical circuit images. We propose a new data set, CircuitVQA, with 5 different question types. We do extensive evaluation of various state-of-the-art vision language models. We experimented with several kinds of input formats, OCR text, along with, of course, the image and the question, OCR text, bounding boxes, detailed description of relevant circuit components, and so on. And we find that BLIP with the component description sort of provides highest VQA scores across most question types while having one of the lowest hallucination scores. Okay, hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.